Hello students. So for this video on inverses, you're going to learn what an inverse is, how to find the equation of an inverse, and how to draw the graph of an inverse. And you'll also understand what the term one-to-one means. Okay? So anyway, as I was saying, inverses. All right, so one key characteristic of inverses is that they have reflectional symmetry. So that was my attempt at sort of reflecting myself on a camera and in a lens, whatever. I don't know if it worked. But anyway, if you have two graphs that are inverses, you're going to know they're inverses if they have reflectional symmetry over the line y equals x, the parent linear function. All right? So that's one characteristic you got to keep in mind. If two graphs are going to be inverses, you can tell pretty easily just by looking at them if they are mirror images over that line. All right, so one problem we'll start with is the equation. The first thing in the packet I'm going to hand you in class, or the sub is going to hand you in class, if you're given the equation y equals the square root of x plus 2 and then minus 3, right? Square root function. We're gonna pick this apart, and we're gonna make sure that you're able to find the equation of its inverse and also to graph its inverse. Okay, and the order you do that in really doesn't matter. If you're really strong with graphing transformations, then you might want to just graph it first, and from the graph to be able to write the equation of the inverse. All right. So okay, let's start by just sketching a graph of this function. Right. So all right, you know what? Because I gave you a grid. Or a table rather, on your packet. Let's actually fill in a table here for this function. So, all right, -2 is a good number to choose for x, -1, 2, maybe 7. You know, any number for x is going to make the square root of what's under the square root into a perfect square. So -2 is going to give us 0 minus 3 is -3. Plugging in -1, we'll get -2. Plugging in 2, we get -1, and then plugging in 7, we get 0. So if you plot these points, -2, -3, on your grid, it'll look nicer than it will up here. That'll be the end point. -1, -2 might be there-ish. 2, -1 might be here. 7, 0 might be there. It's going to look like this. And from class, you know the shape of the square root function is going to be a half of a sideways parabola, right? Just to review that. Now, we can also talk about this function's domain and range, right? We will in a minute. Or you know what? Let's actually jot that down right now. Domain and range. So the domain, -2 to infinity, and the range would be -3 to infinity, right? That's for this function. All right? Now, if we're asked to sketch the graph of the inverse, I'll use a different color to show that. Let me just see. Did I? Okay, I did use the notation f of x. I'm sorry. So let's change this to f of x. That's better. Remember, f of x is just a fancy way of saying y when it comes down to it with the equation. But the nice thing about using this notation is we can label. If I ask you to label the curve or label the function, somewhere along the curve, just write the little f, and that'll show that. All right, now let's talk about sketching the inverse first. All right, if we're sketching the inverse, kind of like how we derived the log function from the exponential function, was just flipping x and y, right? Flipping the x and y, those ordered pairs, and redrawing it, you would have the inverse of a function. So logs and exponents are a perfect example of two inverse equations. All right. So for the graph of the inverse, do I have room to put it over here? Barely. Graph of the inverse, we're going to plot, instead of -2, -3, -3, -2, and so on. All right? If we plot those points, and then we connect those dots, we'll have the graph of the inverse. All right? So -3, if this was -2, -3, -3, -2 would be about here. And this is all easier if you have the grid, right? -2, -1, then 0, 7, you know, and so on. It's gonna look like this, right? If you plotted enough points, you would see that is the graph. And when you have two equations that are inverses, you can tell, again, as I said earlier, you can tell pretty easily that they're inverses because they have reflectional symmetry over the parent linear function y equals x. Y equals x is this diagonal line, right? So if two functions are inverses, they are mirror images over that line, all right? So the way you draw an inverse, just to repeat myself, the way you draw an inverse is from the original graph, just switch x and y, replot the points, and you'll have the inverse, all right? And you can always check if you're good at visualizing, just kind of tilt your head and make sure that there is symmetry over that line, right? Now, to find the equation of an inverse, we can now, one thing you could do is looking at the graph of that red function, could we find its equation? Yeah, it's a little bit tricky, but that this graph is half of a parabola, all right? So the inverse of a square root function will always be half of a parabola, all right? And the way you indicate that in an equation, if you're writing the equation of the inverse, now there's two ways to find the equation of the inverse. One way is to do it algebraically, which I'll show you next. But right now, to find the equation of the inverse, we're just using the graph we drew. All right. So this is if you draw the inverse first to find its equation, sometimes it's easier. All right. So knowing this is half of a parabola, the full parabola would continue like this, right? It's only half, but it does have a vertex, -3, -2, right? This endpoint here was -2, -3. And the parabola's vertex would be -3, -2. So you have a parabola that's been shifted 3 to the left and 2 down. So we have x plus 3 squared, if you remember that, and then -2. Now, that will be the entire parabola, right? So the one thing that's a little bit new here, or the additional thing that's new here is, how do we tell the graph, or whoever's drawing this, that we only want this half? And what you have to do is just state a restriction on the domain, all right? So you write the equation. We're going to follow this quadratic function, but only on the domain where x is greater than or equal to -3, all right? So only on the domain of -3 to infinity, all right? So that's how you show a parabola that's only half, right? Only half the parabola would be to write the full equation, yeah, but we're only following those points for x values more than or equal to -3, all right? So that's how to find the equation of an inverse using a graph. Now, I could give you other functions than just square root functions, right? We talk about cubics and cube roots and so on, but just using the graph of this one in particular is a little tricky. So that's why I chose this one to do as an example, all right? Because the square root's inverse is only half of the parabola. We haven't talked about that before, so I wanted to give you this one. All right, let me show you the algebraic way to find the equation of the inverse, all right? So if you didn't want to use the graph, if you wanted to do it by hand using algebra, just a different way, no problem, all right? And I'll show you how to do that. So we have the original function, which this is really y, right? Y equals, I should write this in black so it's not confusing. So this is how to find the equation of the inverse just by hand using algebra, not using a graph, right? It's easier in some ways, trickier in others, right? So now the first step, if you're finding the equation of an inverse algebraically, would be to switch x and y. That's the theme of inverses, switching x and y. The domain and range get switched, the ordered pairs get switched, and the equation, x and y, get switched, all right? But when I ask you to find the equation of the inverse, this actually is the equation of the inverse, but you would never leave x equals. Right? That's not considered explicit form of an equation is y equals. We always want to solve this for y. So now we've got to get the y by itself. We've got to solve for y. So we have to undo everything that's being done to y, right? Just like solving any equation. So you're kind of thinking about PEMDAS backwards when you're solving an equation. So start by adding 3. And by the way, if you understood the equation from the graph, that's great, but you should know how to also find the equation of an inverse by hand. So this is also important, even if you prefer the first method. So we add 3 first, Next, we have to undo this square root, right? The square root is by itself. How do you undo a square root? We have to square both sides of this equation, all right? The left-hand side, you're going to leave as x plus 3 squared, all right? Expanding it and writing x squared plus 6x plus 9 isn't wrong, but for this unit on graphing, this is the form we want. That'll tell us there's a shift 3 to the left, right? We want that form. We don't want it expanded. So don't expand. And this, squaring a square root, they are inverse operations. They undo each other. Right? So we have x plus 3 squared equals y plus 2. And now one last step is to subtract 2, right? So we have x plus 3 squared minus 2. That is the same equation we got from the graph. All right? Now, doing it algebraically, the one limitation of this is that the restriction on x doesn't naturally happen. All right? So you have to really just remember, for square root functions, the inverse is going to be a quadratic, but only on a restricted domain. So now that is the full parabola, right? This red equation is the full parabola. So now you got to go back and check the graph and say, oh, okay, no, it's only where x is greater than or equal to negative 3, right? Like I had before, you have to write that restriction in here now, right? Now, not to give you too much new stuff in one video, but one trick to this, if you have trouble knowing how to write the restriction here, you can always keep in mind that the domain and range always gets switched, right? So the domain of the inverse is going to be negative 3 to infinity, and the range is going to be negative 2 to infinity. So just keeping this in mind, this is the function, the original f, and this is the inverse. Am I still on the screen, sort of? Yeah. So if you keep this in mind, then the domain of the inverse is really what you're writing down for the restriction, right? This is, I don't like the y equals on this side. Literally. All right, so y equals this, and then you just write down that domain. So in other words, to generalize this, you can always just keep in mind that the restriction on the function's domain is always going to be the same as the range of the original function. The range of the original function is the same as the domain of the inverse. So that will always be true, right? Now these quirks though and stuff, they really only apply for square root functions. The other ones are a little bit easier. Right? You don't have to worry about a restriction for a cubic and a cube root. Right? It's only for square root functions where this happens. All right, see how I'm doing on time. All right, the video's getting a little bit long, but I'll mention a couple of other things about this. All right. The one other term I wanted to make sure I went over is the term one-to-one. All right. A function is one-to-one when its inverse is also a function. Okay. A function is one-to-one. So this black function f is one-to-one in this case. Its inverse is also a function. If you remember from other classes, what it means to be a function visually is that it passes the vertical line test. All right, so if you draw a vertical line anywhere on the graph and it hits more than once, it's not a function. All right, I mean technically what it means to be a function is that for every x value on the graph, there's exactly one y value. Right? That's the technical definition. But visually, we know that a graph is a function. If you draw a vertical line anywhere on the graph and it hits just one time or no times, it's still a function. If it hits more than once, then it's not a function. All right? So function f is a function, of course, yes, but it is also one-to-one because its inverse is also a function. This graph, right, that is a function. That would pass the vertical line test. All right? So when a function is one-to-one, we can use this notation to indicate its inverse. So the best answer for the equation of the inverse in this case is not y equals, but is f inverse of x equals x plus 3 squared minus 2 on the domain x is greater than or equal to negative 3. Or you know what, I'm just going to write the inequality. It's a little bit easier. In this part of the unit, it's a little bit easier to use an inequality symbol, just for me, I think, than to write the interval notation. All right? So we only can use this notation, f, that negative 1 is not a negative 1 power, that's just the symbol for inverse, all right? We can only use f inverse of x, that notation, instead of y, when the original function is 1 to 1. All right? The original function we know is 1 to 1 because the graph is an inverse, is a function. All right? So we can use this notation. All right? So if the inverse was not a function, like if it came out to be like a circle or a sideways parabola, so the vertical line test wouldn't pass, right? Then we would just leave y equals. All right? It's a technicality, but if the inverse is a function, we can use this notation. If the inverse is not a function, we have to leave just y equals. All right? So this is just one example that I wanted to go over. It's a lot of new stuff in one video, I know, but hopefully this will allow you to at least do the problems in the packet that require you to find the equation of an inverse and to graph the equation of an inverse. All right? Thank you, and I'll see you all soon.